Hello! Have you ever wondered how to do timing down to the picosecond level in a large particle physics detector system? Have you ever wondered about the do's and don'ts in precision clock distribution? In this video I will tell you all my secrets, so stay tuned. Hello and welcome to this IEEE Nuclear and Plasma Science Society educational video. My name is Stefan Ritt. I work at the Paul-Jarry Institute in beautiful Switzerland. We do lots of experiments at our particle accelerator here. The experiments require extremely precise timing down to the picosecond level, like the Mach 2 experiment which you see here. In this video I will show you how to design a picosecond precision timing system for that experiment and teach you all lessons I learned in the last 10 years or so. But let's first start with the basics. Assume you want to detect a particle decay. The particle might decay into two particles which go in two detectors. They generate an electric signal and that goes into electronics where you can measure the difference between the two detectors. If you have now two particles, they usually do not decay exactly at the same time. So the first decays and then the second. You again register the signals in your electronics, but now you measure a different time. Now if you have a large system, you might require quite a number of clocks. Assume you have n detectors on the left side and n detectors on the right side, and you want to correlate each channel with each other, then you need n square clocks. Assuming you have 1000 channels, you need 1 million clocks, which is just too much. But you can do a trick there. You can use a reference clock. So each channel has its own clock, and this clock measures the time against a common reference clock. In this case, if you have 1000 detectors on the right, 1000 on the right, you only need 2000 clocks instead of 1 million clocks, which is much less. Then the timing accuracy plays a crucial role. So on the left side you have the detector system, and there are various sources of time inaccuracy, like different length of cables. So if your cables don't have the same length, the signal might arrive at a slightly different time, and it's called skew, which is the channel-to-channel variation. On the right side you have now the clock distribution, and if you have to distribute the clock to many channels, you might need a repeater in between. Now a repeater can introduce some variation of these clock edges from period to period, and this variation is called jitter. And now to make a good timing system, you want to get the skew as small as possible, and you want to get the jitter as small as possible as well. In the next couple of slides I will talk about the Mach 2 experiment here at PSI. So on the left side you see a sketch of this experiment. We have a muon beam coming from the accelerator, muons get stopped and they decay. Usually a muon decays according to the standard model in the so-called Michel decay with two neutrinos. We are looking now for the neutrino-less decay, mu2e gamma, and that's where also the name Mach comes from. This is forbidden in the standard model and would be a hint for really new physics. In the Mach experiment we aim to search with a precision of down to 10 to minus 14, a really high precision experiment, and that requires us to distinguish a single particle decay from several particle decay with a precision of about 10 picoseconds at the electronics level. To design a clock distribution systems, there are several options. One obvious, of course, is GPS. You all know from your mobile phones, from your car, global positioning system. And that works with satellites going around the globe and sending signals, and with a lot of corrections you get down to an accuracy of like roughly 100 nanoseconds, but this is not enough for the experiment I was talking about. Another very well adapted scheme is the so-called White Rabbit, and I put here the reference for that. That does timing over standard Ethernet, which is very beneficial because you have already Ethernet for data readout. It follows the IEEE 1588 standard, which is the precision time protocol, and can distribute timing over thousands of nodes and tens of kilometers with about 100 picosecond accuracy. But again, 100 picosecond is not enough for the Mach 2 experiment. You also have fiber optics, and fiber optics can give you timing down to a few picoseconds, but the fiber only works point to point, so you still need kind of the distribution of the clock to many channels. So how to achieve timing at the picosecond level? I will talk now about single-ended versus differential lines, PLL jitter, clock stability, some noise reduction strategies, timing calibration, and all lessons I learned in the last 8 to 10 years in the MEC2 experiment. So let's start with the very basics. Voltage noise causes timing jitter. That's very important to understand. So if we have an electric signal here and there's a clock edge, every clock edge is not infinite fast, but it always has a certain rise time. If you receive this clock via a buffer, then this buffer has a fixed receiver threshold. So only when the clock surpasses this threshold, then the buffer triggers and the output goes from 0 to 1. Now if you have some noise, the noise shifts the whole clock signal up and down, and the rising edge of the clock crosses this threshold a little bit earlier or a little bit later. This is now called timing jitter. So it's important to understand that timing jitter always comes from voltage noise in a clock distribution signal. Now, how big is it? So you can do a rough estimation. So we have here a noisy signal, we have here our threshold. The voltage noise, delta U, is here, the timing uncertainty, delta T, is here, and from this triangle you can do this simple calculation. You solve the equation for delta T. And for typical values like 2.3 volt in a system, rise time of 1 nanosecond, then you get at a voltage noise of 10 millivolt already a timing jitter of 3 picoseconds. So it's really important to get your voltage noise as low as possible in order to achieve the picosecond accuracy. So one trick you can do there is use differential signals like LVDS, low voltage differential signaling. So what you do is your signal goes to a buffer, and this buffer sends a positive and inverted copy of your signal, which might be a sine wave here, but it also might be a clock, sends 2 copies to the receiving side. It's important that these 2 electric lines, they are really close together. So if any noise is induced on this line, the noise is induced in the same way in a positive and on a negative signal. If you then do the subtraction on the receiver side, this common spike here gets removed, and that's very nice. There's, however, a common pitfall. Like you might here have your signal and the signal, and again you go differentially. But if you get now any noise in this little path here of this signal and the signal, then the differential signal doesn't help you, because you get down here an inverted version of your noise, and if you subtract the 2 signals in the end, you get back your noise here. So it's really important to have no path of a non-differential signal here in between. And that might be, for example, even an FPGA. So an FPGA, even if it has differential inputs and differential outputs, internally it always works only single-ended. So FPGA is very poor for clock distribution in that sense. So as a typical rule of thumb, whenever you have a clock and you go through an FPGA, even if your clock at the input is perfect, you get at the output a jitter between 50 and 100 picoseconds. So don't use FPGAs for low jitter clock distribution. Optical signals, of course, are much better, because you cannot have any electrical noise on them if it's optically transferred. But even the optical transceiver, which you see here, the sender and the receiver, usually they also have a short path of non-differential signal, even if they have a differential input and output. So it's important to really carefully check your optical fiber transmissions, not to receive any noise here at the input or at the output, which also could cause then timing jitter. So careful with optical clock distribution. What kind of clock stability do you need? Well, GBS, I mentioned already, you need this for experiments which are far apart. So assume you have typically astronomical experiments, or here neutrino experiments which are hundreds of kilometers far apart. There it's almost impossible to have a clock distribution line for over many hundred kilometers, so use GPS for this, and you are happy with your 100 nanoseconds of accuracy. Do we need an atomic clock? Yes, you might need an atomic clock for high precision time measurements, but only for very long term measurements. So if you want to measure over microseconds or seconds or even more, then you need a long-term stability. In particle physics, however, when you measure decay of particles, you don't need a long-term stability. Typically, your measurement times are in order of 10 nanoseconds, right? Two particles decay and they decay different directions, so it's just a couple of nanoseconds apart. So you only need a good clock stability during this few 10 nanoseconds. So assuming you have a clock stability of 10 to the minus 4, and with this clock you measure a time of 10 nanoseconds, then you get a final accuracy of 1 picosecond and you are fine. So excellent low jitter clock distribution to all detectors is needed, but you do not need in particle physics typically a long-term clock stability. Okay, in the next slides I will talk about the wavetakt system which we developed for the MEC2 experiment. Just as a first glance, we have a wavestream board which does all the waveform digitizings from the detectors. We have a special crate there, and then this goes to the overall experiment where we actually digitize about 9,000 channels with 5 gigasamples per second and 12 bits of resolution. So everything starts with a low jitter quartz. But this is not a fancy quartz, it's just kind of out-of-the-box quartz, which has an accuracy here, if you can read it, of like 50 ppm accuracy. And this is this 10 to the minus 4 accuracy, which I told you, which is necessary for this kind of measurements. The nice thing with this oscillator is that it has already an LVDS output, so we don't have, again, the single-ended to differential conversion. It comes already out of oscillator, and it has a very low jitter in a region here you can see down to a few picoseconds. So we use this simple quartz. It's even not in a thermal controlled environment, just a damn simple quartz, and it's good enough for our case. Then I told you the LVDS clock distribution. It's very important to have everything differentially and not single-ended in between. So we use here a commercial clock distribution chip, which you see actually the actual picture. And the nice thing is of this clock distribution, it has a differential input and a differential output here on the right, like a 1 to 10. But internally it's completely differential. So it avoids any single-ended path inside the chip, which could introduce additional timing jitter. And actually even the data sheet claims that the added timing jitter of this chip is in the order of 200 femtoseconds. So it's really very good for low jitter clock distribution. Okay, so let me come to phase lock loops, PLL. We sample our signals with the DRS4 chip, which has actually an inverter chain of 1024 inverters. And with this we open some analog memory cells to sample the input signal. This inverter chain works like a voltage controlled oscillator, and we lock this to an external reference clock. And if there's a phase difference, you get these up and down pulses with a loop filter, RC loop filter, and then the speed of this voltage control oscillator is controlled in such a way that the frequency of this chip is exactly in phase to the external frequency of the reference clock. And the loop filter here has a typical time constant tau of R times C. Now in the PLL you have two kinds of jitter. Assume you have here a perfect clock on the top part, and then you have here the output of the PLL. You have two kinds of jitter. The first is the period jitter. The period jitter is now the variation of the width of one period to the next period or to the other periods. And the phase jitter now is the jitter of all the edges versus the perfect clock here on top. And these things are not necessarily the same. They're kind of correlated, but they're two different things. If you have this loop filter in a PLL with the R times C, you can have it slow or you can have it fast. On the top here, you have a slow PLL filter. And that makes the periods, very close to each other and only slowly, breathing, going wider and narrower. So the period jitter is very, very small in that case. But the phase jitter might be large because it only reacts slowly, and then you might add up some phase variations towards the reference clock, and that's what can kill the timing resolution. So what you really want is a fast PLL. So even if your period jitter then, differs largely between one period and the other, the phase jitter, meaning the edge versus the perfect clock, is kept as small as possible. So it's very important that if you tune your PLL in such a timing system, that you don't tune for the period jitter, but that you tune for the phase jitter and make this as small as possible. Now, it's not only the loop filter you have there, but you also have jitter caused by a non-stable power supply. So if you have here, one of these cells of the PLL in the domino chip, you have here on top a power supply. And the power supply might be noisy. Like for the DS4 chip, a 1 millivolt noise on the power supply causes already a 10 picosecond jitter at the output. So it's very important to have a very low noise power supply. On the boards I showed you already, we have to use a switching power regulator, and these are usually noisy at the output. So what we do is, you filter the output to get the output at least amount of noise here. And you do it with the RC low pass filter. If you make the RC low pass filter big enough, you can really nicely filter even the noise from a switching regulator. But something people mostly don't really know, I didn't know it for a long time, is that each capacitor here has what is called an equivalent series resistor, ESR. And this is typically in the order of like 1 or 2 ohms, and can be just the leads leading into the capacitor, or the internal metal inside the capacitor, which has some resistance which is not zero. So if this RC filter now wants to filter your power supply, there has to be actually some current going into the capacitor and some current going out of the capacitor. If the ESR now is non-zero, you have a voltage drop there, and this voltage drop induced by this current shows up as a variation of your power supply, and that can actually kill you. So I did make a very simple SPICE simulation. I have here the switching regulator, and then R of 10 ohm, 100 microfarad capacitor, and then here I put in the equivalence for the ESR of 1 ohm. And even with a simple SPICE simulation, you see already that you get a noise, a remaining noise at the outside of like 8 millivolts. And 8 millivolts here, that kills you already. If you use, however, a very low ESR capacitor with 0.001 ohm, then you get only 0.1 millivolt noise here, and that's what you need. So it's very important to use low ESR capacitors for all power supply filtering. That's one of the crucial tricks. And yes, there are capacitors on the market. So like this polymer aluminum capacitors, which you see here, they actually have up to very large capacitances of hundreds of microfarads, with the resistance here 10 milliohm or even less. That's very nice. And for the R here, again, you don't want to have a too big resistor, because then if your power consumption varies, you have here more or less current over this resistor R, and again that makes a drop in your power supply. So you want to have this as small as possible. So what we use for our design are these EMI suppressor filters, which work very nicely for this ripple filtering here, and you see here the response versus frequency. They are basically just a capacitor and 2 little coils, but they have internal resistance of only 100 milliohms. And then that's again very good to keep the power supply filtered but stable, even if the current consumption of your circuit varies over time. Okay, that's the overall picture and a part of the schematics of the wave-dream board, which we use in the MEC experiment. And you can see here, so this this low ESR capacitor here. This is this suppressor, the suppressor filter, the EMI suppressor filter, which I showed you here. And you have here actually even the switching power supply, the switching regulator on the PCB. And with this filtering, even having a switching power supply on your board makes still a very good power, generates a very good. So even then a switching power regulator with this filtering can produce a very nicely filtered low noise power supply, which you then can use for your PLL and your timing on these electronics. It's important to have a good ground layer and a power supply layer. So you see here, that's our ground layer on this board. And actually there are 2 schools. One school says you need an analog power and a digital power, and you keep them separate, and you only connect them at one point in the power supply. And the other school says, just do one huge single ground layer and connect everything to this one. So we tried both and we came to the conclusion that the single ground layer is better. So we use this for our design. Then it's very important to fight the electromagnetic interference, EMI. So when we take waveforms with our board, you see sometimes here some spikes here in the waveform, and you can even see here these are some specific frequencies. So you need very carefully to shield everything which generates EMI in a way such that you put some housing around some circuits which produce radiation. That if you have very fast digital signals, that you even put here some slew rate limiter. So this is for some one-wire sensor, we use it there, which has a very fast rise time, which produces EMI. So just by putting here a capacitor to reduce a little bit the rise time, the EMI is reduced dramatically. And then another very important thing is you carefully have to check every digital chip in your design and measure how much EMI it produces. This usually is not written in the data sheet, you have to measure it yourself. And it's not obvious which are good and which not, so you have to just measure lots of them. And we use actually an oscilloscope probe with a little magnetic sensor here, and which we put on every chip and measure and only hand select those chips which produce the least EMI and only put those on our electronics. This slide shows you another trick which we use, which is kind of a specialty for the DRS4 chip. So the DRS4 chip has a PLL here which is rather long, so it has 1024 inverters. And if we have a sampling speed of 5 gigasample, the whole window is like 200 nanoseconds long. That means, however, that the phase detection and correction only kicks in after one cycle of the PLL, which in that case is like 200 nanoseconds. And then the phase comparator kicks in and corrects the phase to the correct external high precision reference clock. Now if we have an event inside this window and you measure the timing of this event relative to the beginning of the sampling window, you integrate already quite a fraction of this uncertainty when you do this timing measurement. So on average, you get something like maybe like 25 picoseconds average error. To mitigate this problem, I designed in the DRS4 chip a 9th channel, which we use as a timing channel. So we sample 8 input signals, and on the 9th channel, we sample this low jitter, high precision clock running at 100 megahertz. And now the trick we do is we measure the timing of an event not relative to the beginning of the sampling window, but relative to the next edge of this high precision clock. Now this high precision clock, we know this edge is correct, so we only integrate a much smaller fraction of this uncertainty. So you see the slope of this line and the green lines, it's the same, but we just integrate a much shorter section of this green line, and therefore we reduce the timing inaccuracy from this original 25 picoseconds down to less than 2 picoseconds, and that's really makes a big difference for our experiment. If you want to learn more about calibration of the switch capacitor array, I refer you to this publication here where we describe all the details how you can do the calibration of this kind of chip. These are all the basics, and now we build a full system for the Make2 experiment, and we call this the WaveDuct system. So let me quickly run you through the system. My goal was to make a small, compact crate, but with some few tweaks. So I don't want to run the trigger and the clock distribution at the front part, which is used by some of the standard like VME systems. And I want to make this whole thing very compact, so the cooling doesn't go from bottom to top, but it goes from back to front, so we can just stack one crate on top of each other. My goal was not to make this specific to Make2 in any sense, but being a bit more general, like a more general crate standard. So I took all the great things which are on the market, like SPI serial bus for configuration. I put the trigger and the busy and the clock signals all to the backplane, which you can see here, so we don't need this front panel cabling for daisy chaining. I added dual star gigabit links for data acquisition, hot swap capability, And I put this famous now 5 picosecond low jitter clock right on the backplane here. On the right side we have a kind of a shelf manager with its own Ethernet interface, which produces the power, 400 watts, fan control, board management, so we can even do firmware upload to all the boards, and we can reboot each slot individually through this kind of a crate controller. This slide shows now the clock distribution on the backplane of the WaveDuck crate. So we have here the master clock and the fan out, as I showed previously. Then on each crate we have a data concentrator board which contains a jitter cleaner and then distributes the clock on the backplane, and you can actually see here some snaking, so all the lines going to the individual slots have this roughly the same length to within like 100 picoseconds. And here you see the real layout of the backplane, and you see all this snaking here in pink, so that the clock arrives roughly at the same time on all of the boards. This is how an actual picture looks like, and here you can see the funny backplane with the holes inside the backplane, so that we can actually blow air from the back to the front for the cooling. And here you see the crate with some slots. We have here the data concentrator board, and we have the trigger concentrator board, which is would be a topic of its own. The WaveStream board housing the DS4 chips you have seen already. So we have here some input amplifier which can actually digitize, which can actually sample signals from silicon PMs and amplify them with up to a gain of 100. We have a high voltage biasing also for silicon PMs, so they can be operated just with this board and no other hardware. On the board we have 2 DS4 chips which are read out by ADCs, and the ADCs also digitize with the 80 MHz the input signal continuously, which we use then for triggering in the FPGA and on a global crate and system level. This is how the whole system in MEC 2 looks like. So we have the WaveDuck crates here. In the MEC 2 experiment it's like now 9,000 channels, but it would scale up to 16,000 channels if one would need that. We have a local trigger. The trigger information gets passed to a global trigger here, which makes, for example, a cut on the calorimeter by adding up signal from 4,000 channels from the calorimeter and then putting an energy threshold on the calorimeter. On the other side, we have then the trigger and clock distribution crate, which sends the trigger and the clock via bus to all the 37 crates we have in the MEC 2 experiment. So this is how the actual system looks like. The WaveStream boards are placed here in the WaveDuck crates. They are cabled up here. And here you see actually an actual measurement from the calorimeter. So we have here a 900 liter liquid xenon calorimeter where the photons with 52 MeV impinge and then create some light. And you see here the front face of the liquid xenon calorimeter. You see here, which has like 4,000 silicon PMs on almost 1 square meter. And then you see the light distribution of the shower. And actually you see in this case that you have actually 2 gammas impinging, and you can nicely discriminate between them. Now we did the full jitter measurement of the global system. So you have here this little quartz where the clock starts, buffer, the jitter cleaner PLL, and then it goes through this distribution crate, which you see here, then to the data concentrator board in each crate, then through the backplane to the WaveStream board. So we measured the jitter between all this point in this table, and the jitter measurement is not very easy. So actually we only could do reliable measurements if we use differential probes on a high-speed oscilloscope and actually solder the probe to the measurement point to have stable conditions. So here you see the list of the measurements, and the important ones are those here. So slot to slot, we have like 1.9 picoseconds in one crate, and between 2 crates we measured like 3.0 picoseconds. Now for the global calibration, it's important to understand that even if you try to make a perfect clock distribution, you always have an uncertainty coming from the detectors. The cables between the detector and the digitizing electronics never have the same length to the picosecond level, and also the clock distribution is not perfect to the picosecond level. Now some people, they do some signal injection somewhere at the ADC, which calibrates for this, but that does not calibrate the length of this distance between the detector and the ADC. So what you actually need is to use physics event as a global calibration. So you have to find some event which is registered in all the detectors together, and then you can measure the timing of the same event and calibrate for all these uncertainties. So some experiment, they use a LED flasher, shining light at the same time to all the detectors, maybe having different light paths here, but you know this from geometry and you can correct for this. In the MEC experiment, we mainly use also cosmic events, which go through the whole calorimeter and light all detectors, and then we can correct for this efficiently, and we actually really get down into the picosecond level. So this shows here the MEC2 timing detector, which consists of 256 little tiles, 4 by 6 centimeter, made of plastic scintillator, and read out by 2 crates of 512 channels of the waveframe board. These tiles detect the positrons from the mu2 gamma decay, and usually in a single event not only one of these tiles is hit but several, and you can see here some real event with the 2 tracks. So depending on the number of hit detectors, we get here the timing, and on average we have between 6 and 8 tiles being hit, and then we reach here a level around 35 picoseconds. So these are the lessons we learned in the last kind of 10 years to build this thing. So designing a new crate standard, you might think it's crazy, you make your own crate and that's much too much work. But actually it turned out not to be so complicated. If you're just on your own and no committee or something like that involved, it's pretty easy to define the things, and if you know what you're doing, it's actually not as hard as you might think. Distributing this 5 picosecond jitter clock is also not so hard if you just follow these few basic things which I've shown you here. And actually doing the whole crate from scratch can kind of simplify things, because you don't have to follow any historical requirements, and just use the best parts for everything you use there. So the shelf manager here is nothing complicated. It's just a simple 8-bit microcontroller with just a few hundred lines of C code, and that's enough to run the whole crate. And the cost is kind of like $2,000, including the power supply for the whole crate, which is much cheaper than like a VME crate or something like that. What, however, we found is really the tough work is this mixed signal boards, the wavestream board, where, because we have this gain of 100, we only can accept 40 microvolt of noise at the input. Everything above this we would see in our waveforms. So this actually took us 6 years of development from the first idea, with like 2 people more or less working continuously on this project. The analog front end with this gain 100, this switchable up to gain 100 stage alone was like 1.5 years to find the right parts, to do the layout correctly so that the crosstalk in the noise is as low as possible. Also the DC-DC converter needed quite 4 revisions to find the right device which has the lowest EMI, as I shown you previously. And the more noise sources you find, the more new ones find and fix, the more new ones you find which are just like hidden below the bigger noise source. So lots of experience was gained, and much of this experience is not actually present in textbook, and that's why we have this lecture here. So let me conclude with the recipe for precision timing in large systems. So rule number 1, use differential clock distribution everywhere. Careful filter the power of all the PLLs with a low ESR capacitor. Whenever you use a normal capacitor, you won't get this performance because the noise on the power supply would be too big. Then carefully identify and remove any sources which make noise in the system and replace them by either other parts or make some kind of shielding around. And then actually you can in the end really do a system with the 5 picosecond, actually less than 5 picoseconds overall system accuracy. Wow, you made it all the way to the end of the video, so you must be quite interested in this topic. If you want to know more, don't hesitate to contact me, and my email here is below. Please also consider to come to one of our Nuclear and Plasma Science Society conferences, like the Real Time Conference, which happens every 2 years in spring, or to our flagship conference, NSS MIG RTSD, which happens every year late October, early November. In these conferences we discuss precision timing in real-time applications, but much more in this field. So you will meet people with similar interests, and that can be really quite inspiring. Actually, most of the things I showed you today in this video I learned from one of these conferences. So please also consider to become a member of IEEE and NPSS, so you will get access to many more other resources in this technical field. Thanks for your attention. Maybe we meet one day in person at one of these conferences. Take care.